Hi everybody, I'm Kai. I'm going to talk about a project I've been working on recently, one of them. It's ERE, stands for Extended Regular Expressions, which you may know if you've used any of the POSIX, regular expressions utilities. ERE is one of their regular expressions flavors. And so the project's about, compiling those at build time with proc-macros so that you can run them at runtime pre-built. But first, some background. What is a regular expression or a regular language? Formally, a regular language has all these options. You have the empty set, the empty string, simple, and then you have concatenation of two regular languages, alternation of two regular languages, or a clean star, which means 0 or more repeated of regular language. And if you've taken a computer science class, you might have seen that. But in the real world, we more see things using these syntactic sugar, where you might have a quantifier, so you have 4 of them, or you have plus, which is 1 or more, question mark is optional, and then these bracket things that are ranges, characters. And so most of the time, you're using one of these libraries or another one if you're using another language. For Rust, it's the regex crate by Burnt Sushi, who's did a lot of work. It's really vast, so I've got a lot to catch up on. But the primary way that these run, slide on this, yeah, is that at hello.
Yeah, that interference, I think, is radio interference coming from something that broadcasts periodically. I don't think it's anything we're doing.
There's some meetup of radios going on right now.
This is police office headquarters, so yeah.
Okay. Anyway, so first thing that these libraries will do, and actually first of all, just for the regular expressions thing, this is the regular expression here. I guess I should show them here. And what this regular expression is doing is it matches, first it finds an open single quote, then it matches all non-single quote characters until it reaches another single quote. So for example, in this text, it'll match quote, Citizen Kane, end quote, and then this backslash s means any white space, and then plus means at least one or more of the white space. So that will skip this white space here, and then it will match a open parentheses, and then 4 digits, and then an end parentheses. So it will extract here, you can see Citizen Kane, 1941, with the quotes, brackets, and everything for parentheses. But the main thing to note here is, first of all, this is compiling at runtime. So when you call regex new, that's not a const function. You couldn't really compile a regular expression at const or with const because there's just a lot of string manipulation and allocation that needs to be done when compiling a regular expression of any complexity. And then normally that isn't really an issue because it should be pretty fast to compile it, and hopefully you're only compiling it once every run. But what it does mean is you have to include the entire regular expression compiler in your binary, which can be quite a bit. Another thing that you might notice here is when it runs captures, that is not on instructions in your binary, that is on a data structure in your binary, which means there's going to be overhead in terms of running a sort of VM-like system over the data structure. It also has a dynamically sized output because obviously at compile time you don't know how big the output is going to be, so you're basically returning I think they have captures object, but it's basically like a vec, which means that you just need to hope that, or you basically need to hope that you don't accidentally try to access a capture group that doesn't exist. And then finally, we don't like this unwrap. It probably doesn't matter because hopefully you test your regular expressions, but if you didn't, then that unwrap will crash your program, and there's no thing at compile time that will check to make sure the regular expression is valid. And then another background, I actually learned about these while I was working on this project. There's a thing called lexer generators. Most popular known one is RE2C, which is basically a little executable that will, they also do output to Rust, so also Orita to Rust, that will take these like common things in your code and replace it with equivalent regular expression implementation. So instead of doing it at runtime, it does it like while you're writing the code, and it'll insert code into your file that will run or be equivalent to the regular expression you specify. But screen changed. Okay. But the downside, of course, with this is it's not very ergonomic because you gotta like run this script and hope that you don't change your regular expression. Anyway, so introducing ERE, which is the library I made. This is a QR code to the GitHub if you want to check it out while I'm talking or anything. But so here we can see a great difference in syntax. First of all, it builds at compile time. So this exclamation mark means that this is calling a proc-macro, actually any macro, but it is a proc-macro, which means that this is passed into it not as a string, but as a token. It's just like the actual source code. And then it'll parse that string from the source code, and it will build equivalent code to regular expression that gets inserted there, where the compile regex macro call would be. And then the next thing you might notice is that, so it'll call the compile regex code equivalent to the regular expression, but it doesn't need to serialize over data structure. It's instead just instructions directly in the binary. And then also it knows the size of the captures at build time. So here I have it specifying three captures. There's the implicit one that captures the entire input, or the entire expression, and then that's capture group 0. And then there's capture group 1, which is the name here, and then there's the capture group 2, that is the date. And as you can see, since it's fixed size, we can now do a, I don't actually know what that's called, but the thing where you like let an array and it will unwrap everything. Destructuring, that's what it's called, yeah. So first of all, I guess just stepping back a bit, what are proc-macros? So proc-macros are basically a feature of Rust that allows you to define a function in a special proc-macro crate that will take basically tokens from the source code and replace them with new tokens that are generated based on those tokens. And it can do a whole lot of things. So you can actually run code, access files, even send web requests at build time. But for this one, it doesn't actually have any side effects. It just internally processes stuff. And so, sorry, go ahead.
Could you explain what a token is at a really high level?
Yeah, so when the Rust compiler, or the pretty much any compiler, I think, is going through your source code to build it into the program, it's going to go through and find each like individual piece, so maybe a variable name, a keyword, literal, such as a string or a number, and it's going to turn that into a token. And in Rust, I don't know what it does under the hood, but for the what's passed to the macro is essentially a enum value that's like, okay, this is a literal, and then inside the literal it'll say it's a string, or literal string. I don't know if that's the core thing, but anyway, the main libraries that use for this typically are sim, as in syntax, which is a really nice library for handling like parsing of token streams, and then also quote, which allows you to basically write the code that is going to be inserted. And then you have these like little hashtag interpolations that get included as if it were a format string. Yeah, but generally the idea is that returning this compile regex call, it gets replaced with some code that's generated by this function. Anyway, but about the name of the library, I called it ERE because I ended up picking the POSIX extended regular expressions flavor or standard to implement. This is a bit closer to pure regular expressions than, in some ways, than like your JavaScript PCRE standard. This is PCRE standard, and most things implement something related to that. But anyway, extended regular expressions don't have back references, and they don't have word boundary assertions, which are also not features in the more theoretical version of regular expression array languages. But one downside that I did learn was that POSIX defines its own ambiguous submatching standard, which is hard to implement, rather than the more greedy approach of the PCRE kind of standard. And I'm going to talk more about that near the end, but for now, just know that I'm just sticking with the greedy one that you probably see in most languages outside of POSIX utilities for now. But I'm going to eventually have to implement that because the name's a promise, and so I gotta go with it. Anyway, but so in terms of actually building the thing, when I started off, I was kind of like, yeah, this is going to be easy. It was not. So this is kind of generally the process that it goes through to, or that I go through to figure out how to build code to, or equivalent code to a regular expression. So first of all, this starting part is pretty similar to a runtime regular expressions library. In that we're going to parse our regular expression. So this one matches US phone numbers, optionally with the +1. And requiring the dashes, I guess. And it'll turn into an AST. So it's an abstract syntax tree. So for example, this is basically a concatenation of this like parentheses capture group optionally, and then concatenation of 0-9 ranges, so any digit number 3 times, concatenated with a dash, and then the 3 more digits with a dash, and then 4 more digits, and then here at the beginning and end we have the start anchor and the end anchor, which basically tell it that the string should start at the beginning of the input or the tested string, and it should end at the end. So there shouldn't be any extra space at the beginning or end of the string. This should just be the entire string as a phone number. And so I guess it turned into a syntax tree, which is basically, it's a tree with all the different components. Yeah, similar to most compiler things. But the main thing we're getting into is Thompson NFAs. So Thompson NFA is probably the standard way for converting regular expressions from the tree-based format into a kind of state machine. And here we can kind of see the different components. The general idea here is that within NFA, you, at any given point, are in one or more states, and given the next input, you can move to one or more states from, or 0 more states technically, from each of the states you're already in. So unlike a DFA or any other, I guess, where you normally think of the state, machine, you're going to be moving, you're going to be multiple states at the same time, which is why it's non-deterministic finite automata rather than deterministic finite automata. And these are, NFAs are basically equivalent to regular expressions, which is why we use them, because graphs are nice. But additionally to this, I guess, first of all, just here in this diagram, you can see all of the components with the Thompson NFA that they converted. So any concatenations turn into the first state machine followed by the second state machine, and then any alternations are like first state machine split into the second state machine, you enter and then you split into two different states. So you have two different states active at the same time that each will be run, and then those of them that pass are going to continue on. And same with the question mark, which is optional, star, which is 0 or more, and then plus, which is 1 or more. The main thing is that we are turning this regular expression into some kind of state machine that is, you can imagine it as like a multi-threaded state machine. And additionally, because we aren't doing like pure NFA, we also have these capture groups, right? Which we need to remember where that was. Like, where along the path did we pass through that open parentheses? Or also, where do we pass through the start anchor? Because if we just did regular NFA, you'd like step through, but you might not, like, I guess, NFAs only know where they are currently. They don't have the global knowledge of, okay, we're at the start. So we need to add in special epsilon transitions, which basically means 0 symbol transitions that will consume, or that will basically be assertions that we are at the start or end. And then additionally, with NFAs, they don't have, or they assume that we are matching the entire string, typically. So we need to add in special implicit loops at start and end to represent that we could start anywhere and end anywhere, which is the way that most regular expressions in practice work, rather than the pure regular languages method, which would say we're matching the entire string. But those loops will be excluded if we have the start and end anchor, because then we'll know that we'll never have to loop through anything to reach the start of the string, or start of the match. Anyway, that was, it's not changing. Okay. That was a lot of talking, but it's probably easier if I just show it. So for example, take this expression. So it, first of all, this match needs to start at the start of the string, which we see the main that. And then it will capture either A, B, or A, C, and then 1 or more D's, and then optionally an E. And then since there's no end anchor, it can have any number of characters after it, but those will not be included in the match. And so this is actually the original thing that we get out of the original NFA that we get out of the Thompson NFA construction, but that's really complicated, so we optimize it down into this. And as you can see, we start at the beginning, and then we're going to, no, okay. Let's skip to this one. So we're going to start at the beginning, and, this is slow. Just wait for it. There we go. We're going to start at the beginning. We're at the start state, and the point we are at the input, actually this is one of the engines that I have, is flat, lockstep, NFA. So the reason it's flat is that all epsilon transitions occur at once, and the reason it's lockstep is that all threads are always at the same point in the input. But I'll just show that on the diagram, I guess. So we start, sorry, do you have a raising hand?
Oh no, just
okay.
Scratching my eyebrow.
So first we're going to do the epsilon transitions. So that is going to go to, this is slow. I guess, so we're going to go past the first open parentheses, which is kind of implicit, it's not actually shown in this, but the 0 capture group always includes the entire match. And then we're going to have the assertion that we're at the beginning of the string. If we weren't at the beginning of the string, right, where you have the beginning of the string here, then it would not continue on, and in which case it would reject because there would be no active states. Then we're going to pass through here, which will set the 1, which is this, the first capture group open bracket, or parentheses. And then here we have 2 paths we're going to go on, which means we'll have 2 active threads. And as you can see here, if you look closely, this one is epsilon 0 and this one is epsilon 1, which signify the priorities. Because if we ended up in finishing with 2 active threads, we want to know which one to take the capture groups from. But so we end up here after the first epsilon transition. We haven't consumed any symbols yet. Then we take one symbol transition. So in this case, it's an A, which both of them actually start with A. So both of them will continue on, take symbols. Then an epsilon transition again, which actually won't move because there are no like epsilon transitions to go through. We're just already at it. So the next one is a symbol transition. Once it goes, we consumed a C, which means that the top thread up here didn't continue on because it doesn't have a C to consume, it takes a B, but the bottom thread continues. And then again, with the epsilon transition, we're going to pass through the end of the capture group index 1, once this goes, there we go, which means that will be added to the thread so that we now know that, and those are all recording the indices at which we pass through them, which means that we know that the beginning of capture group 0 and 1 occur at index 0, and the end of capture group 1 occurred at index 2. Yeah. And then I guess we're going to do another symbol transition. We're going to go through the D here, which is required 1 at least by their expression. And then we're going to do the epsilon transition, which is going to give us a huge number of states. And as you can see, they all have their own priorities. So with epsilon 0, we go here first, which has the lowest or highest priority. Then we're going to go through the epsilon 1, which is going to give the next priority. Then we're actually going to go through epsilon 2, which is going to go further propagated to the second priority, which is actually the accept state. But since we're not at the end of the string, we're not going to do the accept. And we're also going to end up here, which is lower priority since propagating out from state 14, we go through the higher priority epsilon 0 out of state 14 first, which means that state 13 has the lowest priority. And all of these threads will have the same capture group field set except for thread 2 since it passed, threads 2 and 3 since they passed through the end of capture group 0. Anyway, long story short, only 2 states will survive going through the next D symbol transition. This one actually matches D, and then this one is the end loop that will match any character. So this is basically an empty negated set, which means it will end up here at Q14. And then we're going to keep doing that on and on. But I'm not going to make you sit through that because this is slow. But anyway, it's going to end up with this kind of match statement of which state it's in and what the next character is in. But that's operating over characters, which are a bit of overhead to decode every single character and match. It'd be much faster if we could just do this over U8s. So instead of decoding chars into between 1 and 4 bytes for UTF-8 code points, we could do every single byte and just decompose every character range into the individual ranges of U8s that we could have. So here's actually the full, this chart is the full process for matching any one Unicode or UTF-8 code point. It's pretty complicated, and so I'm glad I don't have to write that myself. But I guess the code I wrote will convert from chars into UTF-8, which will add a large number of states if you're not using only ASCII in your regular expression. And that also includes if you have like negated sets, because if you say anything that's not an A, that includes all of the UTF-8 code points that aren't an A, which is like a lot of them. But anyway, we're splitting multi-byte characters into multiple states so that we can go through each byte in that appropriately. We're going to combine similar sequences with the same kind of optimizations we did with the character-based TDFA. And then there's various other optimizations that I do. I'm not going to go into details on that. Switch. And so there's a similar engine to the flat lockstep NFA for chars that's for U8s here. It basically is going to be faster because you don't have to have the overhead of decoding chars, but it will be larger because there's going to be more states since there's more bytes and more paths through each code point, basically, to like up to 4 different states for a single char, just because you have to handle with the 4 different bytes. And so, yeah. But that's the main thing here is that will be included in the binary size, since all of this is getting compiled into the binary rather than just being a string that gets compiled at runtime. Anyway. Oh, I should go fast. Okay, so another engine I have, basically, I'm sorry, step back. The ERE will, depending on the properties of the regular expression that's passed in, it can select one of these engines that it thinks will be the most efficient, or best fitting, or whatever you want to optimize for. Currently it's just fastest. But in this case, one-pass regular expressions are a subset of regular expressions where there's no more than one single transition at each step. So before we had that case where it branched out and then there were 2 transitions at the same time that both matched an A, that would not be one-pass regular expression. And so you can also think of it as the cases where the power set DFA only has states representing one NFA state. We're talking more about DFAs in a bit. If I don't know. Yes. No, it's okay. Whatever. But the important benefit here is that we're going through the NFA, but only ever have one thread at most, which means we don't have to handle duplicate threads or thread priorities. We're just going through one at a time, which is faster. Yeah. So for example, this one, cell 4, it's not one pass, but I said, yeah. Here, with the A's, they will both match at the start of the string, which means that we will have 2 different threads active at the same time. And then again, here, if you are at state 10, for example, then you're going to go through epsilon and then back through D. Then if you're also at state 10, then you can go through all these epsilons which don't consume anything. And you're going to match this, which will also match a D because it matches everything.
I had a question.
Yeah, go ahead.
When you say threads, are you saying conceptual threads, or does that also mean like you implemented it, it's creating like a process thread?
No, these are conceptual threads. So it's basically for the NFA or flat lockstep NFA engines, it's a basically a vec of like a stack of enum states that.
So it's single threaded is how it typically.
Yeah. Because I think there'd be so much overhead just to start up threads for text matching, unless you were going through a massive document. But anyway, so the next one, this one, actually wait, this is really slow. Okay, this regular expression is one pass, and it looks complicated, but really what it does is it matches numbers optionally with a decimal point in the middle. But really, the reason it's one pass is that we are split across this dot. Meaning that we're going to be matching, sorry, no, this isn't the same one. This one is domain names. So it matches, it's not perfect regular sort of domain names, but it matches dashes and then alphanumeric, and then it has one or more sets with a dot and then another domain segment. But since it's separated always by dots, it always knows whether it's continuing the current domain segment or if it's transferring to this next one, which means that there's never any point where there's ambiguity in which thread we're going through, which means that we never will need more than one thread, and there's a lot of optimizations to do off of that. We'll see. Ooh. All right. There are two separate kind of implementations that this turns into. The first one is the match-based implementation. So in this one, first of all, the state at the top is not a vec in this one because there's only ever one state at most. But we're basically just going to match what the current state is and what the next character is. And optionally, this if I equals 0 just means if we're passing through a start anchor to assert that we are at the start, then that's the additional condition. It'll just set the next state, which this one's actually really fast, especially because we get the benefit of being compiled. You can get through a lot. The problem is it would be faster if we could immediately jump to the next thing instead of having to check in the next loop which match condition or match case we're at. So the other implementation is a function-based implementation, which has basically state 0 and then it only matches on the next byte rather than having to match on what the current state is, which means that we can always jump to the next state. So for example, here we are calling func state 4, which will then run whatever conditions we need to check for when we're at state 4. And this also means that we can potentially have states that check multiple bytes. For example, if we have a sequence that never diverges, so let's say for let's say we just want to match a static string as part of it. We want to match red, let's say, inside of a larger expression. When we get to that state, it'll just match the entire sequence red instead of having to call for each byte, which is another advantage of this function-based implementation. The downside is that until the become keyword is standardized, it has potentially unbounded stack growth if the compiler doesn't decide to include tail call optimization, which is why for most cases the library will prefer the match-based implementation even if it's slightly slower. And then finally, how much time do I have?
We can run until about 8:10.
Okay, I'm gonna go fast.
That wasn't fast.
I might have over-prepared. I don't know. Anyway, so lastly, we're going to be converting the last intermediate state is the TDFA, which is a system where instead of having multiple threads, we basically combine all the combinations of possible threads into a state, which is the power set DFA construction. Notably, since we have these tags with different priority orders, in addition, unlike a normal DFA, we're going to have or normal power set DFA, we're going to have individual states based on the priority. So if we have a state that represents state 1 in the NFA and then state 2 in the NFA, and then we have another one that has 2 as higher priority than 1, those are going to have to be separate DFA states rather than having it be set-based. And then also the power set conversion for NFAs to DFAs is worst case exponential size, which means that we have to bound it, which means that not all cases can become DFAs, even though they're faster, since you don't have to manage multiple threads similar to the one pass. It just potentially is a lot more states. So here's an example. I guess this is the NFA at the top, and this is the DFA. The additional metadata basically with these capture groups and anchors is included here. I just didn't include in the diagram, but it's going to instead of having all these epsilon transitions that we're going around, we're just immediately on the next transition matching some character and then including the capture group tags in that data. And so this means that we're basically doing one transition at every byte and ending up in one state at every byte rather than having multiple states at the same time, which is going to get messy. Although, again, it could have potentially much higher DFA size, more states, since, for example, in this one, we have one state that represents both 3 and 6, rather than individual states, just having it represented separately. Yeah, the main thing here is that each of the DFA states represents the tags for all of its individual NFA states within. So, for example, 3 and 6 would have 2 fields. I'll just say 2. Where the way I represent this is the state will have this old tags field, which is an array with the size of the number of NFA states it represents. And then for each of inside of that array is another subarray that is for each of the capture groups that it has, which means we're basically tracking all the same data you would be tracking with the NFA, just inside of an individual DFA state, to remember where all the capture group beginning and ends are. And then there's one last engine that is kind of a meta engine. That runs test on cases where the capture groups are at fixed offsets into the matched text. So it runs tests on it, which is just a Boolean of whether it matches or not, and then it can afterwards index it, which means you don't have to maintain the indices of where all the threads match their texts all the way through. We just say it is a match or not, and then index in and grab out strings. Right, what's next? First of all, the POSIX ambiguous submatching is something you have to still do. With this example here, the current greedy approach will prefer, so with this ABCD, it will prefer to first grab the A for this capture group, so we get A, not the AB, because A is earlier in the alternation. And so it'll pick A, and then the B will end up at this question mark. And similarly here, we will end up with AB and then B, because we have 2 Bs, which means that the only possible match is the AB here, rather than this case where it could be A and then B, or it could be AB and then no B. But also separately, with the POSIX standard, once this loads, it says that for these alternations and there's various other things that it says, but this is one of the big ones, is that it should pick the biggest option, like the longest one. So it's going to pick AB always, which is it turns out there's no linear time way to implement this that is known. Obviously, this doesn't actually matter for test because we don't care about capturing which submatch we capture. We're just going to say this is or is not. So there's an equivalent in that case. And then one-pass regulations also never have ambiguous submatching, which is what kind of defines them that they never are going to be multiple threads at once. But yeah, the POSIX standard is easier to describe, but harder to implement and less efficient. So that's something I'm still working on. Another thing I'm still working on is with the become, I mentioned earlier, become keyword stabilization. It essentially can allow these functions to act like go-tos to each other instead of having to either rematch every loop or rematch the current state every loop, or have without, or depending on what the compiler decides to do, could have unbounded stack growth. And then finally, the current way I'm defining regular expressions, or the current usage, I guess, method, is that you have this object, the regex object with some constant generic of the number of capture groups it has. But the problem here is that it's always going to have this option that says we might or might not have a year, right? But we know from this regular expression at compile time, which is when it's compiling, that any match is always going to have a year because that's how the structure of the regular expression is. Which means that really we don't need that option there. We could have for example, a struct, once this loads, that says this one matches an RGBA value, optionally with the alpha. We could say that the entire match will always exist, or if there's a match. The R will always exist, the red will always exist if there's a match, the blue will always exist if there's a match, the green will always exist if there's a match, but the alpha may or may not exist if there's a match. And this is actually implemented currently as we have a feature flag because I haven't decided on the actual interface yet, but this allows for a lot more like static definition and reduction of unwraps potentially that kind of scraps that itch. Yeah. Oh, also, I think it was just some slides, but if I skipped over it. With the regex struct, it basically is just a struct that contains two function pointers. Whereas with this strategy, we could directly implement them as like an impl block on the struct that we're adding it onto, or as a derived helper for a trait. Optionally, I haven't decided on the exact semantics of how I'm going to do that. Anyway, does anybody have any questions? This is the GitHub project, and then I'm also looking for a job. If anybody knows, so that's my LinkedIn. You can talk to me after.
I have two questions. I haven't seen this before. I've been looking for a compile time regular expression crate for a long time. So I didn't even know this existed. I've been looking for one, so this is awesome. And you should definitely, there's like 2 issues on the Rust regex crate where Burnt Sushi said, I can't do this, it's too hard. So this is really impressive because Burnt Sushi said, I can't do this, this is too hard.
Well, so when I was really making this, I think I saw some of those things. And I don't think they said it was, yeah, they said that or you said that you've been looking through, or for, I guess, a compile time regular expressions library, and mentioned that Burnt Sushi on the like actual regex crate had said that they weren't going to be able to build a compile time version. I don't think it was that it's too hard necessarily. There are some complexities, but I think the main thing that they said on those different threads was that, and I did mention, one of the downsides of this is that you actually can't compile at runtime because everything is proc-macros. So being able to have that be compatible with the existing Rust or regex crate would be nearly impossible, which is why they were ruling that out for the regex crate. Go ahead. Yeah. I guess, do you want a microphone? That might be easier.
Is this working? Yeah. I guess my next question is, have you done, what would be really fun is just to see like runtime comparisons of your crate running. Because I know from the project, my little open source project that I've been working on, that one of the big savings you get is the regex compile time. So that upfront cost is now just at compile time. So it'd be really fun. I don't know if you have on your crate website, but it'd be fun to have like a little table of comparisons of how yours.
Yeah, so I mean that's hard. I've been currently all the benchmarks I've done them on my laptop, but what I've found so far is that my library is faster in cases that are like anchored, and then it's like where the match is the entire input string, but it's slower in cases where you are searching through a large haystack for some text. And that's probably just I haven't implemented good strategies for implementing or searching in haystacks because I'm primarily focused on the short match case. But yeah, it's always more to do.
Are there any opportunities where you can do like really expensive tests? Sure. Thank you.
Like, is it possible or practical to do something really dumb and expensive? Like, I don't know, just like try the regex on 100 different engines and see which one's faster, and then we pick that one because it's compile time and get away with it. Like, have you done anything like that?
They're
Is that just silly?
So I kind of thought about that, and the main issue there, I think, is that like you could probably add like a macro attribute that's just like when you're compiling this, spend as much time as you like. But the time it takes really depends on the like input you're giving to the regex expression, which means that you have to like also specify a list of example inputs, which means that the attribute definition would get like several lines long. So you probably could, but it's also, at least with the current engines I have, pretty clear cut. Like there's a hierarchy of the lockstep ones are the slowest, but they're the most general case, and then the one pass and fixed offset are the fastest, but very limited cases. Actually, one pass, most like real world cases, if you have start and end anchors, probably match the one pass case, but obviously you can't just only support that, so we've got the other cases as well. But yeah, the hierarchy definitely means that currently, and this will possibly change as we get more engines, but currently it's pretty clear cut which one's the fastest.
It seemed to me like you were paying attention to making it look nice for the user. What was your design process for that? Did you, like, do you have sample code using reg expressions in your kind of like or writing documentation even before people are reading it? Kind of, what are your thoughts on that?
I mean, I don't know, I kind of put it in like, this is what I would want to use. I don't know, the main idea was like, it should tell you everything up at front at compile time, and after that it should just be like functions you call. But beyond that, I mean, there's like documentation on like the crace.io page. But yeah, a lot of it just came out of like, once you have functions to call, what's the most convenient method to call them? And that's it. Actually, with the current way with the regex struct is probably actually not super convenient because you have to like define this whole like, ooh, just get back. You have to be like defining const something, which potentially can cause like copying. Well, I don't know why you would. I guess they're just function pointers, but recompilation maybe. And it also, I don't know, I don't think it's very nice currently, but the hopefully future struct, or even enum possibly, you could have like this set of cache attributes could be matched, or this set of cache attributes could be matched, and internally you could possibly figure out that it is an exhaustive set of which cache attributes could be matched. That's my other idea, but that'd probably be a little more complicated to do visually.
So it's good to be thinking about things that turn into something nice to read and write.
Yeah, the main idea here is making regular expressions fit nicely into the Rust type system, which seems to have come with some other benefits. Anybody else? Guess we do have to go.